All right, so for my project, I did music recommendation system. So the problem is, let's say that we want to build a recommendation system for music based on a user's input. So how do we do this, and where would we even start? Luckily, Eric Berhardson, a former Spotify employee, has already implemented a music recommendation system that uses approximate nearest neighbors recommendation engine called Annoy. So a little bit about the overview right here. So first, we start out with our audio data set. This includes YouTube videos specifically. Then we want to pass it into the Max Auto Embedding Generator, which is a tool that helps convert raw WAV files into byte strings or vectors. Then the vector is passed into a recommendation engine, also known as Annoy, right here, um, which is, as I've stated, approximate nearest neighbors method implemented by Eric Berhardson. What it does is it takes the given vector, then splits it out, neighboring vectors, which can then be translated back into music. The recommendation engine will then recommend the closest values to the original piece of audio or song. So a little bit about the audio data set is basically this entire thing right here. The entire JSON looking structure is just one sample video out of thousands in the data set. The video ID right here is basically just a YouTube URL ID, and then the start time and end time right here are the two timestamps, and in this case it's 6 and 16. So this would be the 10 second chunk that will be used. And then the labels right here are tags that are given to the video. So for example, some of the tags would be music, guitar, talking, dog barking, etc. These labels are stored in a list. So lastly, we have the feature lists. It lists every part of the audio that is encoded. Um, every part of that audio is encoded into. They're all 128-bit feature strings. So, for example, if we have a 10-second piece of audio, we are chunking that 10-second piece of audio into 10 chunks of 1 second each. And each of those seconds are encoded into an array of 128 numbers, also known as a byte array. This is then repeated for each second of audio, so we will have 10 lists at the end. Next is the Max Audio Embedding Generator. This is going to read a WAV file and then get the corresponding embeddings. When it generates an embedding, it's going to take the WAV file and output it into a JSON file. So let's say that we extract the embedding. We want the audio length to be cut at 10 seconds. We want to make sure that every audio clip is the same size. So in this case, each embedding will be a 10 by 128. So we then want to flatten it so that we have a single vector of 1,280 dimensions that represents a single WAV file. So then when the compressed representation, when it's compressed, we can find the cosine similarity between the two sounds. So for example, if the cosine similarity is higher, that means the two vectors or sounds are more quote unquote similar. So two examples given in the code were birds 2 versus birds 1, which gave us a cosine similarity score of 0.906, and then we had jazz guitar versus just regular guitar, which gave us a cosine similarity score of 0.893. Obviously, both scores are pretty high, which makes sense because they're basically the same. They're basically just different types of the same thing. So right here is a sample of a cosine similarity matrix provided in the code. So as we can see, right here is the guitar versus the jazz guitar. And the lighter the color, the higher the cosine similarity score is. So as we can see, 0.89 is one of the lightest ones, meaning that it's the highest. And then on the opposite end of the spectrum, we have 0.69, which is one of the lowest. And you can see that is just the regular guitar versus a train. Intuitively, this makes sense because guitars and trains sound very different from each other. So we're now able to have a set of these byte vectors, which we can then pass into the recommendation engine or annoy right here. So the recommendation engine, Annoy, this is the most important and complex part of the recommendation system. As I've stated already, Annoy uses approximate nearest neighbors for recommendations. The reason for this is because it's much faster than trying to do a brute force linear scan. So this slide deck actually wasn't made by me. It was made by the creator, Eric Berhardson, but I really like how he explains this, so I'm going to use his slide deck, obviously with my own words. But so let's start with the embedding space, which is just the white space right here, and let's say that each X in the embedding space is a song. So let's say that each X. So now let's pick any random two songs in our embedding, then draw a line between them, and then split the line with a perpendicular line right here, like shown in the picture. Now we have two separate halves. So next, let's choose two songs above the perpendicular line and two songs below the perpendicular line. And then split both of them again with perpendicular lines. This picture right here is what we're going to get. And then let's do it again. And then we get this. And then one more time. We repeat this process basically until we end up with something that looks like this. So this is a partition of an embedding space that we can also format as a binary decision tree, as shown right here. So the top point would be the start where all of the songs are in one embedding space, and then every node is where the space was split. So we keep doing this until we end up at the circular leaf nodes right here. They're differentiated between the squares, and the circular leaf nodes correspond to the blocked off sections, or each one of these sections right here. So let's say that you want to find the nearest neighbors of a particular song. What do you do? How do we do that? So let's say that the actual song in the embedding space lies somewhere within this white circle. So the question is, should we just traverse the tree, which corresponds to that particular region or leaf in the decision tree? So the answer is yes and no. The reason for this is because, as we can see, there are many small x's close to the red x here that we chose. However, since they aren't in the same region as the red x that we chose, they will not be recommended. And obviously, this all happened arbitrarily because of a random split. So this isn't good, but we can fix it. The way we fix it is by traversing both sides of the tree instead of just one side. So now we have 5 other regions that could potentially be our nearest neighbors. So if we highlight these 5 regions in the actual space, it'll look something like this. So this tells us that if we input a song, which is the red X, it'll recommend all of the songs in the 5 highlighted regions. So the problem now is that the song recommendations are formed by just one tree. So for example, all 3 of these could be trees that we get at the end of 3 separate iterations. However, it's always better to have multiple trees so that by random chance we won't be missing certain songs. So the more trees we build and take into consideration when making the decision for determining nearest neighbors, it becomes much more concrete. So for example, again, let's say that the red X is the song that we input, and then we get the set of songs in the purple region right here for nearest neighbors, and then we use the same inputted song in a different iteration, and we run Annoy again, but this time we get random splits going in different directions right here. So we end up with a set of points in the yellow region. Lastly, we do it again, and we get different splits and end up with a set of points in the red region. So let's say that we wanted to recommend 10 songs for a single song that a user inputs. In our example, that would mean that there are 10 songs in each of the purple, yellow, and red regions, respectively, giving us 30 total songs. However, some of the songs are overlapping. So what can we do about this? So let's say that out of the 30 songs, 12 of them are duplicates. Now we take the union and remove all the duplicates. We now only have 18 songs remaining. Since there are only 18 songs, we can actually compute the raw distances for every single one of the 18 points. from the query vector, aka the song we want recommendations for. And then once we do this, we can sort them in a ranked order of nearest neighbors slash nearest distances. So we then find the nearest neighbors of all 18 points from the query pointer inputted song, and then we can eliminate the 8 furthest, giving us the 10 closest songs. And yeah, that's it, guys. That is it for the overview of the music recommendation system.